Hi, this video is about the areas between two curves. It's one of the application of integrals. That means what we will do, we will try to find out how to compute the area between two curves. Let's consider the region which lies between two curves, f of x and g of x, and some limitation, the vertical limitation from a to b. One of the things, please notice, function f of x is greater than g of x for all of the values on the interval from a to b. And now the thing is, how can we compute the area between two curves? Let's look at this situation this way that we were looking in section 4.1. We were trying to approximate the area under the curve. Now we have the approximation of the area between two curves. That's mean what we did. We did divide an interval from a to b by n strips, n sub-intervals with the equal base, delta x. Okay? That's mean now we're doing exactly the same thing. And in order to get the area of one rectangle, we have to find a base of the rectangle, which of course is delta x, and height. And in this case, we do have a vertical height, vertical distance, which the vertical distance can be computed as a top curve minus the bottom one, f of x minus g of x at the sample point, if we talk about this approximation. Okay? That means delta x as a base of the rectangle times the height, the difference between the top and the bottom curve. And now, sigma notation means that we're adding all of them. That means this is the height times base. And sigma is showing me that I'm adding all of them. That means this is my approximation of the area between two curves. That means I can have my definition. The area A of the region S as a limiting value of the Riemann sum of the areas of the approximating rectangles is defined this way, because the limit of the Riemann sum represents a definite integral. Of course, we want the end, we would like to have n the infinite, we would like to have the sub-intervals to be infinity. And I can rewrite this definition as a definite integral. That means the area of the region bounded by two curves, f of x and g of x, with this relation, f of x must be on the top of the g of x, must have greater value on the interval from a to b. The area is defined as a definite integral because the limit of the Riemann sum represents the definite integral from a to b and just the difference of two curves, f of x minus g of x. And since f of x is greater than g of x, we will always get the positive value. And even if we have the negative functions, we will always keep this difference, the greater values minus the smaller value. That means the area between two curves, when we will compute, we always expecting a positive answer. That means this is a small difference between finding the area between two curves and directly integrating a function, because the integral could be negative, could be also zero, but the area between two curves must be positive. Okay, and we can see this definition this way. That means the area between the curve f of x and g of x. Of course, we know that is the difference between the f of x minus g of x. But let's see, which means the integral from a to b f of x represents the area under f of x. Okay, represents the area under the function f of x. Okay, is this part, and then I'm subtracting the function under g of x, which means I'm subtracting this part. And the only thing what stays is the yellow part, or I can say the golden part, the area between F and G. That means this is definitely true definition. Okay, that means let's use our formulas and let's find a few areas. Find the area of the region bounded by parabola x squared plus 1, bounded below by the line y equals to x, and bounded on the side from 0 to 1. That means we do have a parabola x squared plus 1, it's just the x squared lifted 1 unit up. We have a blue line, which is y equals to x, and the limitation from 0 to 1. That means this is simply an integral, definite integral from 0 to 1, the top curve minus the bottom one. The top one is parabola x squared plus 1 minus x dx. And we can integrate, we can finish this, but we all know how to integrate because this integral required only the direct antiderivatives. Antiderivative for x squared, x cubed over 3, 1 is x is x squared over 2. Substituting upper and lower limit. Oh, I think I shouldn't keep my limits anymore. 5 over 6 is the area between two curves. Okay, let's look at the second question. Find the area of the region enclosed by two parabolas. First parabola is x squared, and the second one is 2x minus x squared. That means, first of all, we can see that something is missing. The limits of integration, like what is the interval that I have to integrate, I have to find the area at. That means we have to find out these points, and these points will be the points of the intersection. Another thing is I have my relation. I still don't know which function is greater, but I can see that this is parabola open up because the leading coefficient is positive. This parabola is open down. That means I'm assuming that these values will be below, these values will be above, but we have to perfectly sketch the graph of both of the parabolas, find the points of the intersection, and see what is really the region enclosed by these two curves. That means points of the intersection means that one curve must be exactly the same like the second one. What are the points? X squared equals to 2x minus x squared. Let's add x squared to both sides and subtract 2x. I factor out 2x as a common factor, and then x is 0 and x is 1, which means x is the same like y, 0, 0, and 1, 1. That means I have my blue parabola, which is just x squared, and I have the other parabola, the pink one, 2x minus x squared. If I factor out x, I see that x is 0 as an x-intercept and x is 2. Okay, this is giving me 0 and 2. And I know that parabola is open down, then I can just plot the parabola. Now I also know the points of the intersection. That's when we can see these two parabolas create a nice loop, and the pink function, the parabola which is open down, is on the top, has the greater value than the blue one. That means to set up a definite integral which represents the area of the region enclosed is the integral from 0 to 1, the top curve minus the bottom one. Top one is 2x minus x squared minus the bottom one, x squared. And I did integrate, this will be 2x and minus 2x squared. Integral of 2x is x squared, integral of 2x squared is 2x cubed over 3. Substituting 1 and 0, I'm getting 1/3. Again, a positive answer, that means probably I didn't make any mistake. Example number 3. Oh, okay, I do have example number 3, but let's see one thing will be added. we have to be really careful because in order to get the area between two curves, we always have to identify which function is on the top, which function is the bottom one. That's when we may end up having a few points of the intersection, which means after the points of the intersection, function change the position. And we can nicely see here, having a blue curve g of x and the pink curve f of x. We do have one point of intersection and we do have another point of the intersection. That means in order to get the area enclosed by these two curves, I will integrate 3 times. I will create a 3 definite integrals from a to c sub 1, the pink curve minus the blue one, and then between c sub 1, c sub 2, blue one minus the pink one, and the last subinterval from c sub 2 to b, again the f function, which is the pink one minus the blue one. Okay? That's when we can see we have to find 3 different regions. Overall, we will say that the area is defined as the integral of the absolute value of the difference. And we have to identify the relation and then the difference. That means this is the general, most general definition of the area between two curves, the difference f of x minus g of x, but always absolute value. We always taking a positive, just the difference, just the value, absolute value of it. Okay, and let's see the first function. Find the area of the region bounded by the curves sine of x and cosine of x from 0 to pi over 2. That means, first of all, let's find a point of the intersection, points of the intersection. Sine of x is the same like cosine of x. You probably know for what angle sine of x is the same like cosine of x. Of course, 45. But I did divide both sides by cosine of x. I have tangent of x is equal to 1, and tangent for what angle is 1? For pi over 4. Okay, that means I have my cosine curve, and, oh, actually that's cosine, that's sine, and from 0 to pi over 2, we can nicely see the point of the intersection. That's what I will do. I will integrate twice, from 0 to pi over 4, and from pi over 4 to pi over 2, which actually, you might tell me that I can use the symmetry. I can integrate once and multiply by 2. That's also a solution. That means overall statement, overall definition for the area is the integral from 0 to pi over 2 and the difference between two curves. But I have to make sure that it's positive, absolute value of it. That means I will split for 2 integrals from 0 to pi over 4, cosine of x minus sine of x, and addition of the integral from pi over 4 to pi over 2, sine of x minus cosine of x. But as I said, I will multiply by 2 just one of them. And I did pick the first one. You may pick the second one, the blue one is also good. Okay, integral of cosine is sine of x, integral of negative sine of x is positive cosine of x. And the integration, the limits of integration are from 0 to pi over 4. Let's substitute pi over 4 minus substituting 0. Square root of 2 over 2, the corresponding values for 45. Sine at 0 is 0, cosine at 0 is 1. And we can have this answer. And 2 times square root of 2 minus 1 is a positive answer. As we can see, we have to make sure that we're splitting for 2 integrals or more. Okay, another question. Find the area of the region enclosed by the function y equals to x plus 2. Another one is square root of x. I just typed x to the power of 1/2. And we do have a limitation, y equals to 0, which is the x-axis, and y equals to 2 is another horizontal line at 2. That means we can find the points of the intersection, but what I did, I drew the function. I have the graph of the function. That means this graph represents square root of x. This is x plus 2. the y-intercept 2, the x-intercept negative 2. Horizontal line 2 and horizontal line 0. That means this is my region. This part and this one. And we can, of course, algebraically find a point of the intersection, but you can probably guess that the value must be 2. Square root of what number is 2? That means one of the points of the intersection is simply 4, 2, that's 1. We also have this one. We also have this point. I mean, these two are the points of the intersection for the other curve, the line and 2. That means I can say 0, 2. Okay. Okay, that means now we do have a little bit of problem, because we can say we have the first part, A sub 1, the first area, and the second one, A sub 2. That means the first one, because we have to split it, the first one is the line is on the top minus 0, minus the bottom horizontal line. That we can see from negative 2 to 0 is x plus 2 minus 0. Okay, that's my triangle. Or I can simply use the area of the triangle. Okay, this one, the second part, is from 0 to 4. From 0 to 4, the top curve is horizontal line 2 minus the root x. Okay, that means that's nice setup, and you can probably finish this integration. It's no problem. I know that you can find the limits of, you can find the antiderivatives, substitute the limits of integration, and get the answer. Of course, I'm expecting a positive answer. Okay, but what we can do, let's look at this graph, this area which is enclosed by these 4 functions from different perspective. That means what we have. The same picture, the same function, the same picture. And now we can also try to integrate with respect to y. That means this was x and this was y. That means instead of looking at my area this way, okay, because that's what integration means, like slicing and adding together all of these rectangles. That means what we will do, I will try to look at this way. I will try to slice the y-axis, which means I will integrate with respect to y. And we can nicely see I can integrate from 0 to 2. That's my limits on the y-axis. And I can see my right curve and the left curve, which it's not really, I can show you one picture, something like that. I kind of flipped. Oh, that's actually x. And that's actually y. And we can say, I say this is my right curve, okay, and this is my left curve. Okay, I have this one. We can see. Okay, that will be the right one, and this is the left, which I flipped the picture for you because I wanted to show you that this we can consider as a top and the bottom. Okay, top and the bottom, and then we understand. But we can think right and left. Okay, let me come back. That means what we can do, we will try to integrate with respect to y. Let's look at the general definition. That means having this situation that I don't really have like a top curve and the bottom curve, but I have nicely defined the right values and the left values. Okay? That means probably this will be the function x, which is defined with respect to y. Okay? That means not y in terms of x, is x in terms of y. And then I can see my right curve, left curve, limitation from C to D in this case, and then I can simply subtract the area. It's the same idea, the same application, but everything is in terms of y. The limits are from C to D, and then the right equation minus the left one. And that means, please remember, right minus left, or top minus bottom. Okay, we don't have to look at this part, but it's just the right, okay? The right curve, because it's in terms of x in terms of y, and minus the left one. Let's say g of y. Everything must be in terms of y, which means we have to solve our equation for x to get the y values, the y expression. Okay, that means let's come back to this one. We don't have to look at this. This is just flipped if you think it's helpful, but we don't have to look at this. Actually, I can leave it. Okay, let's look at this one. That means I will integrate this way. Okay. Let me put this is the equation square root of x. It's square root of x, but solving for x, I will have y squared, positive y squared. Okay, that's what will be my right equation. Now, the equation on the left-hand side was x plus 2, but I have to solve for x, y minus 2, and that's my left curve. Okay, that's we can see y squared and subtracting y minus 2. And you can definitely integrate. You can get the direct antiderivatives and get, applying the limits of integration, get the final answer. Limits of integration are, because we have to look from this perspective, from 0 to 2. Okay, that means that's another way to. You can still integrate in terms of x. That's what I did as a first approach, but this is also helpful to know that. Okay, let's try to do this question. Find the area enclosed by the line and the parabola. And now we can see it's the parabola the other way, because I can easily solve this equation for x, subtracting 6 and dividing by 2. And we can see I do have y squared 1/2, y squared minus 3. That means this is the parabola, open up, 3 units down, but everything is in the horizontal way. It's function x in terms of y. That means probably, since I have these formulas, I can also solve the second one for x, y plus 1. I can integrate in terms of y to get the area. That means, let's see, points of the intersection. I will put my right-hand side. I mean, I don't know still which one is right, which one is left, but I'm assuming we can, doesn't matter at the moment. But I have my one curve, y plus 1, and I have the second curve, 1/2 y squared minus 3. Let's simplify. Let's multiply by 2 and move all of the terms to the left-hand side. I have nice quadratic equation. I can factor out, and my y values are -2 and 4. And now we know how to draw the line. Okay? The line is, now actually I use different colors. I can change the colors. Blue will be solving for x is dividing by 2 and subtracting 6 and divide by 2. And this one more time is just, oh, no, y plus 1. Okay. As we can see, we have a line. Okay, y-intercept -1, x-intercept 1, or the other way. And this blue parabola, one more time. How can we draw the parabola? We can see -3. That means I did shift everything down. I mean, to the left, I can say. But I'm kind of looking from this perspective. That means I did shift down and open up, open in the positive direction of the x-axis. Okay, that means that's the parabola, that's the points of the intersection, and we can nicely see the right and the left. And that's the points of intersection, which will give me the limits of integration. That means the area enclosed by these two curves is the integral from negative 2. Okay, I'm just slicing this from negative 2 to 4. And the right minus left. Right is just the line y plus 1 minus the parabola 1/2 y squared minus 3. And the same thing, I simplify a little bit. I integrate, substituting upper limit, substituting lower limit, go through all of these fractions and get 18. And of course, positive answer. Okay, positive answer. I'm assuming that this is the most important part, what we're looking for. Okay, what we're subtracting. The rest of them is just the integration that you really master it. And we can actually see this one, will be not easy to evaluate the area, to compute the area through the integral with respect to x. Because we do top curve, bottom, it's the same curve, positive, negative, will be a little bit crazy. That means much, much easier to use the method that we just did. Okay, and let's do one more question. Find the area of the region enclosed by the function x and x cubed. Okay. As we're looking for the points of the intersection, x equals to x cubed, move all of the terms on one side, factoring out x, and then x squared minus 1 is x plus 1, x minus 1. That's we do have 0, negative 1, and 1. Lots of points of intersection. That's what we'll do. I don't have the graph. That's what we have. Since we have 3 points of the intersection, most likely the curves, x and x cubed, they changing the position. That's on one of the subinterval, function x is on the top, and then on the other one, function x cubed is on the top. As we have to get the difference between negative 1 and 1 of the x cubed and x, but we have to know how they behave. Okay. And this one is easy to integrate with respect to x, of course. That function x cubed is a little bit, that's x cubed, and function x is this one. Oh, not bad. That this one is negative 1, that's 1, and this is 0. That we do have a region, and I can say the yellow one, and which one I can use? The dark blue. Okay. And we can see between negative 1 and 0, function x cubed is on the top. Okay. And between 0 and 1, function x cubed is on the bottom. And of course, respectively, from negative 1 to 0, the line y is equal to x is on the bottom, and then on the top from this one. That first of all, please look at this picture, and we're not gonna get the answer 0, because this is the common mistake. We're seeing the same amount of the region, like the yellow and the dark blue, is this looks like symmetric, I hope, but it's the same amount, because everything is symmetric, is the odd, both of them are the odd functions. And you can see, okay, this number is negative, this number is positive, exactly the same, 0. But this will be just the integration. We're not just integrating. We're using an integrals and we're applying the integrals. That means the area must be still positive. You can see I shaded a little bit of yellow and a little bit of blue. That means I do have a region. That means I need a number. As we can see, I will integrate from negative 1 to 0, and I will subtract x cubed minus x. Okay? And what I can do, let's actually see. That means this will be the yellow one. Okay, that's the yellow. And the dark blue is from 0 to 1. We can say 1 and 2. Okay, 1 and 2. Okay, and I believe both of them are positive answer. Oh, I didn't really finish this, but we can try. Okay, this will be x to the power of 4 over 4 minus x squared over 2 from -1 to 0. This one will be x squared over 2 minus x to the power of 4. Let me put the square. And this one is from 0 to 1. And of course, both of them, we have to get the same answer. That's we don't even have to bother and integrate twice. We can just integrate one of them and multiply by 2 using them symmetry. Okay, let me finish the second one. This will be 1/2 minus 1/4 and 0, which is just 1/4. This one will be 0 minus -1 to the power of 4 is 4. -1 to the power of 2 is, -1 to the power of 4 is 1 over 4. -1 to the power of 2 is, of course, +1 over 2, because it's half. Okay, and we can see this value is negative and negative, which will be +1/4. The final answer is 1/2. Okay? We're adding all of them together. A sub 1 plus a sub 2. Okay, this is negative and negative positive. That's it. Please remember, because that's the common mistake, especially seeing questions like that. Okay, that's everything for this section. Thank you.